In the previous video, we finished talking about second order constant differential linear equations. And in this video, we'll discuss generalization to higher order cases. From what we know now, this is relatively straightforward, at least if you completely understand the second order case. A recap. So in order to solve this differential equation with initial conditions, y of 0 is equal to 1 and y prime of 0 is equal to 2, we consider the auxiliary polynomial z squared plus 6z plus 5, which you can easily factor into z plus 1 times z plus 5. So it does, and so does the differential operator, right? So the equation can be written as the composition of two differential operators, d over dx plus 5 times d over dx plus 1 acting on y equals to e to the negative x. Thus, a basis for the solution space of the homogeneous equation is given by e to the negative x and e to the negative 5x. In order to find one solution, we should try x e to the x, right? So if you act with this composition of with this operator on x e to the negative x, we get d over dx plus 5 acting on e to the negative x. We know this action of the first operator on x e to the negative x because these numbers are the same. It's minus 1 here is the solution. Is the solution of this polynomial, and there's minus 1 here, so this x disappears, and then here we get 4 e to the negative x. So one solution to the inhomogeneous equation is given by 1/4 x e to the negative x, and the general solution of the inhomogeneous equation is equal to the general solution of the homogeneous equation plus the a particular solution of the inhomogeneous equation. And now I'm going to find a and b such that y of 0 is equal to 1. So if you substitute into this function x equals 0, we simply get a plus b. And then the derivative, if you compute it, it's given by this function. And then we substitute x equals to 0, we get negative a minus 5b plus 1/4. And this should be equal to 2. And to find the coefficients a and b, we need to solve the 2 by 2 the system of equations with the two variables. You can, for instance, invert the matrix, which is again in case of 2 by 2 matrix, where this is equal 27/16 and b is negative 11/16. So the y of x is equal to is given by this solution. So multiplying by a function is a linear, but the is a linear function by distribution, right? So if you multiply in space on any function with a of x, so like this, then so this is a linear operation, right? Because you can act on f plus g or alpha f plus beta g, and you'll get the linear property. Taking derivative is also linear. We sort of can apply them to high order differential equations. So let's define an nth order linear differential operator to be of the following form. So we take function f of x and map it into this expression. So it's an of x, which is a function of x multiplied by the nth derivative of f plus an minus 1 of x times the n minus first derivative of x plus and so on and so forth, plus a1 of x times the first derivative of x, plus a0 of x times f of x. And this linear map can be denoted with the help of this differential operator of degree n. Now, notice that the operator f goes to d over dx of ax times f of x is also a linear map using the Leibniz rule, using the formula of calculus. And in fact, it's a composition of two maps, right? So you don't even have to calculate. So one is the multiplication and another one is the differentiation. And we know that the composition of linear maps is a linear map. However, they are placed in the opposite order, then sort of as we allow them in the definition, right? So what do you think happens if you switch to order? Now, the answer is that we did allow this operator. So observe that. So if you take derivative of the product of these two functions, that gives you a prime f plus a f prime. So it's a prime plus a of x d over dx acting on f. So in fact, any product of linear differential operators is again a linear differential operator, though some work must be done to write it in the form which is sort of specified in the definition. So here you see the functions are multiplied on the left by the differential operators. So this way, differential operators are d over dx or high derivatives of x, they act on the function first. And then after you took the derivative or derivatives, you multiply it by a function. Definition, an nth order homogeneous linear ordinary differential equation is action can be written as action of the linear operator L on y of x is equal to 0, where this L is an nth order linear differential operator from previous slides. An nth order inhomogeneous linear ordinary differential operator therefore has a non-trivial function in the right-hand side. So let's talk about existence and uniqueness for nth order differential equations. So consider differential operator L as such, and assume that the coefficient functions a and of x are continuous on an interval from some x min to x max, some interval where you study in your differential operator. Now, for any x0 inside this open interval, we can specify values y0, y0 prime, y0, the derivative of the n minus first derivative. And there is a unique function y, which is defined on this open interval, such that action of L on y is equal to 0. And those initial conditions are satisfied, right? So that the ith derivative evaluated at x0 is equal to the corresponding coefficient, yi sub 0. Equivalently, for every x from this interval, the map if x, the evaluation x, from the kernel of this operator into Rn, right? So because kernel, it's the null space, right? It's the space of all functions which are annihilated by the operator L, such that Ly is equal to 0. So if the solution exists, right, it must belong to the kernel of this operator. So the evaluation at point kernel given by this formula is an isomorphism. So make sure you understand this part clearly. Now, note that it's saying something. This is saying something rather surprising. In general, for the collection of functions, there is no reason to expect that recording the derivatives at a point should determine an isomorphism, let alone that this should be true at every point. So the existence and uniqueness theorem is asserting that the kernel of a linear differential operator has very special properties. In fact, it's possible to show that this property characterizes such kernels. So linear property given, so they should be differentiable at least as many times as the order of the operator, as the degree of operator, such that the recording the derivatives at every point in the interval x min to x max determines an isomorphism from their span to the n-dimensional Euclidean space. There is an nth order linear ODE, linear differential operator, such that these functions span the kernel. Okay, now let's talk about Wronskian. So another way to express this using the Wronskian determinant. Given n functions, y through yn, and a point x, we can write this matrix and calculate its determinant. So its columns are formed by all derivatives of each of the function from 0th to n minus first, right? So the function is first derivative, second derivative, etc., n minus first derivative, and do the same with every function and compose this matrix. So it's called Wronskian matrix, and its determinant is known as the Wronskian. So if those y's, they solve an nth order linear differential equation, then this determinant is 0 if and only if these functions are linearly dependent as functions of x. So like in every point x in this interval where you're studying this differential operator, these vector functions are linearly dependent. Well, some Wronskians. Consider functions x and x squared. So the Wronskian is 0. At 0 is equal to 0. So the determinant of this matrix is equal to 0. Right. So it's the x, its derivative, x squared is derivative. But x and x squared are linearly independent as functions. So what happened? Right. So how can you relate this to the previous statement that we just discussed? Well, so as was mentioned before, the Wronskian only works when these functions are solutions of some degree n linear differential equation, right? But you cannot find a differential equation. Yeah. So, but it's hard to find the equation with these two solutions. So now restrict ourselves to the study of operators of the form like this. And let's talk about homogeneous equations. So Ly is equal to 0. As in the case with the degree 2 operators, we can start factoring L into linear operators. So consider auxiliary polynomial of degree n with the same coefficients as in the operator. So let Ri be its roots, and m sub I will be the multiplicity of root Ri. And then, well, we can write this polynomial as the product of the following factors, as we know very well from algebra. The fundamental theorem of algebra shows that such factorization exists, at least if you allow the Ri's to be complex numbers. So this operator factors in the same way as its auxiliary polynomial, right? So these are this is the factorization of L in terms of products of first order differential operators maybe raised to some power, to some powers. Now, it's true because composing derivatives behaves formally just like multiplying polynomials, as we discussed. So those are linear transformations, and they commute with scalar multiplication. As you can multiply by a scalar before or after acting with L. Now, the factors commute, right? So it doesn't matter which order we're down. Any function in the kernel of some collection of those factors will also be in the kernel of L, right? It's the same as if we have a product of numbers and one of the numbers is equal to 0, then the whole thing is equal to 0. Now, we know that the kernel of d over dx minus r is spanned by e to the rx, right? So in other words, e to the rx is a solution of this differential equation, ly is equal to 0. So in the previous video of order 2 equations, we saw that the kernel of d over dx minus r squared is spanned by e to the rx and x e to the rx. And more generally, acting on f of x e to the rx is equal to, you can just prove this by induction, but you can iterate. So it's equal to nth derivative of f times e to the rx. So all of the pn minus 1 e to the rx is annihilated by this operator. So any element from this space is sent to 0, right? Because we have n derivative here, and the way it works, that everything cancels out. Now let's get back to our general operator, in written in general form. So we have seen that. So here we can just well, generalize it and apply and say that all these functions they live in the kernel. So if multiplicities are mi, right? So for multiplicity m1, we'll have e to the r1x, x e to the r1x, etc., x to the m1 minus 1 times e to the r1x. So this is kind of the first family of the first part, first group of elements like basis vectors in the kernel, right? And then there'll be a second one here, and so on. So there'll be as many functions as the multiplicity, and then you write them all together in one set, right? So these functions, they form the kernel. So the total sum of them is equal to the order of the differential operator. So to see that we have a basis of the space of solutions, it remains only to see that these functions are linearly independent. Well, it's kind of obvious, but nevertheless, let's prove it. So suppose that we can actually write down some non-trivial linear combination with coefficient Cij, which is equal to 0. Some of them are non-zero. So without loss of generality, let's assume that ck1 of in front of x to the k e to the r1x for some k is not equal to 0. So if we choose k such that it's the largest number, so we can choose, we can choose k such that it's the largest number such that ck1 does not vanish. And now, well, let's factor it out. Act with this thing first on the linear combination. And then here, all other terms will be written later, will be written to the left. So here is a product of over I is bigger than 1. And then, so the differential operator over here annihilates all the terms for j is greater than 1. Right? So, and it also annihilates terms x to the I, e to the r1x for I which is less than k. Again, by our previous considerations. And the coefficients of the terms for I is bigger than k are 0 by our assumption, because that's how we chose it. So the only remaining term comes from ck1 x to the k e to the r1x. Okay, so let's consider it. So like everything is sent to 0, right? All terms in this double sum, they disappear except for this one. Well, we can calculate the derivative, right? We can apply this differential operator. We get k factorial, right? Times ck1, right? So when you differentiate x to the k times, you get k factorial. Right? Okay. And now we can apply the derivative further. So if we act with this operator over here, so see, we know that those Ri's are different from R1. So it's a simple exercise to show that the action will be reduced to this. So on the there's a typo. So on one hand, this has to be 0, right? Because the linear combination of those elements must be 0, and we just act on it by being, yeah. So I'm going to rephrase that. So this has to be 0 since we got it by applying a linear operator to an expansion which was equal to 0. But on the other hand, this can only happen if this coefficient is equal to 0, right? So this thing is not equal to 0. This is not equal to 0. This is not equal to 0. The whole thing must vanish. So therefore, ck1 is also equal to 0. ck1 must be equal to 0. And that's a contradiction to our assertion. So that means that those functions are all functions in the kernel of this big linear operator, differential operator L, are linearly independent as functions. Stuff linear. Recall that a linear ODE, well, looks something like this. So in this case, the coefficients are not necessarily constants. So a system of linear ODEs is simply, you have several coupled equations. So here you see there's a derivative of y, second derivative of y, the same equation with function x, and derivative of x is the same equation with function of y. So everything is coupled together. And more formally, a linear ODE, single linear ODE looks something like this. So there's a linear operator acting on y of t is equal to f of t. And the system of linear ODEs, what looks like that when this operator acts on vector y of t, so it's equal to vector function f of t, and an through a0 are matrices, matrix valued functions. So the functions are vector valued, right? And the operator is matrix valued. The coefficient functions are matrix valued functions. So it's kind of, in terms of linear algebra, it's a kind of easy to generalize systems of linear ODEs like that. So in the previous example, so we have this linear system. Let's write it down as this matrix differential equation. So you can check that these two statements are equivalent, right? So this matrix, so see, we only taking the second derivative of y, so that's why I have matrix 0, 0, 0, 1, d squared over dt squared, and then plus the first derivative. There's only the first derivative acting on x, that's why it's 1, 0, 0, 0, and so on. So we can turn a single nth order linear ODE into a system of first order linear ODEs. So take as an example, second order ODE, y prime prime minus ty is equal to 0. So it's equivalent to the first order system, which involves a third function z of t. So indeed, you can say that y prime is equal to z of t and z prime is equal to ty of t. So if you just substitute, take a derivative of the first equation and substitute z prime to the second equation, you'll get back the equation that you have started with. Or, but sort of our goal is to go from the second order equation to the system of two first order equations, which you can write as a matrix equation. So the dOdt acting on a vector yz is equal to this matrix 0, 1, t0 acting on a vector yz of t.